In yesterday's lecture, we took a journey to the quantum world. And in fact, the title of the lecture, at least the way I think of it, was Honey, I Shrunk to the Quantum World. Today we're going to do part 2 of that lecture. In yesterday's lecture, we met a number of denizens. Let me remind you of our journey. We began in the world of the everyday. And then very quickly, we decided that we wanted to shrink. And at the level of 10 to the minus 5, well, we hadn't got to our destination, so we continued our trip. At 10 to the minus 10, we had entered the realm of the atom, and there we met numbers of different quantities. There were quarks, there were leptons, and there were the force carriers. Let me remind you that the quarks are kind of shy. We never actually see quarks in the world around us. They hide in the interior of nuclear matter. So if we look at a picture, for example, of a meson, what we see is a bubble-like object that has something inside of it. And those objects inside are the quarks, and they are never free to roam around the world in the way that electrons are. Whenever a quark travels, it has to be inside of one of these bubbles. We call these bubbles hadrons. Any sort of bubble which contains a quark is a hadron. And there are the bubbles like this, which we call mesons, which are actually quark-antiquark pairs, but there are also a different set of hadrons. These other hadrons have quarks not in pairs, but in triplets. So for example, this was our picture of the nucleus of the helium atom. The blue balls were protons, the yellowish one were neutrons, and in the interiors, once again, the quarks are confined. So that was the beginning of our journey to the quantum world. And then in addition to the quarks and leptons, we also found that they were a class of force carriers. And these force carriers had a very interesting role. They had to maintain the quarks, for example, in the interior of protons and neutrons. The force carriers also, in fact, lead to structures like us, because it is principally the electromagnetic binding between atoms that leads to molecules, which lead to biological systems and ultimately lead to us. So these parts of the universe are very important in understanding how life works. Now, the discovery of quarks, in fact, was not a complete surprise. In fact, it's very interesting that when we read history of elementary particle physics, it is very reminiscent of the history of chemistry. In 1871, there was a zoo of elements that were discovered by Dmitri Mendeleev. And at first, chemists were very confused. Many elements were discovered, but eventually Mendeleev looked at the profusion, the zoo, as you might call it, and he imposed order on it. This order we see in high school even today. In any science classroom, one of the things that one is likely to see is a chart of the elements. This chart was created by Mendeleev. One of the interesting things about his creation was not all the elements on the chart were known when he first thought of this way of ordering them. And in fact, he used the fact that there were missing places on the chart to predict new elements. Very shortly after his predictions, these elements were found. In 1964, roughly speaking, the same thing happened. A physicist by the name of Murray Gell-Mann and another by the name of George Zweig looked at the profusion of nuclear matter, not just protons and neutrons, but many forms of nuclear matter. And they found a zoo. And like Mendeleev before them, they imposed order on the zoo by saying there are certain regularities here, and we can use these regularities to make predictions. So that's the world in which we're worrying about. Yesterday, we also talked about spin. We observed that all of the quarks and all of the leptons spin at a certain rate, which we physicists like to call 1/2 h bar. Well, I didn't say anything about the spin of the force carriers yesterday, so that's where we're going to start here, because the force carriers are actually very different. For the force carriers, the rates of spin are not 1/2 h bar, but in the case of the force carrier for the electromagnetic force, they spin at 1 times h bar, twice the spin rate of the electron. In the case of the gravitational force carrier, the so-called graviton, the spin rate is 4 times that of the electron. And now, this actually makes a big difference. Let's review the business that we talked about yesterday about why fermions don't like to be at the same place at the same time. And we can do this with a different graphic today. These green balls here represent fermions. And now let's imagine that we try to push them together, just shoot them out of a cannon. When we do this, even if we turn off all electrical charges, when they approach each other, the fact that they're fermions and no two of them can be in the same place at the same time causes them to be repelled. This is the Pauli exclusion principle. Let's imagine, instead of shooting electrons at each other, that instead we are able to control light with sufficient degree of specificity that we can cause light particles to collide. So what would the experiment look like under those circumstances? Well, once again, we'll use these green balls to represent the photons. And we imagine that we have a device where we can direct these photons directly towards each other. And so now let's watch what happens. They approach each other, and unlike the fermions, they pass right through each other. So this is a very important lesson about the quantum world. In the quantum world, not everything behaves the same with regard to what we call the Pauli exclusion principle. Fermions naturally repel each other, but if you turn off all charges, they still repel each other. Bosons, if they have charge, repel each other, but if you turn the charges off, they don't repel each other anymore, and they are allowed to pass right through each other. We are starting to learn how to take advantage of this behavior because of the fact that they can pass through each other. We can use this as a way to store information. A new generation of computers, in fact, is using this idea. We have these new proposals for what are called quantum computers. A process called entanglement occurs, and entanglement exists because photons, unlike electrons, can actually be brought to the same location and be there at the same time, and therefore information in some sense can be traded between the two in a way that you cannot do for electrons. Our present generation of computers are built on electronics. These new computers, built possibly on photonics and using quantum entanglement, hold the promise to become much more powerful than the computers that we have these days. This is one of the cutting edge applications of science, even as we talk. So now there's another important implication for our universe. This diagram represents an atom. The clouds, the lobes that are in the exterior to the diagram represent the electron clouds. Those lobes are held out there, first of all, because the electrons are charged, but even if we turn the charges off, the electron lobes would still be exterior to the atom. Remember, for a theoretical physicist, when we see a picture like this, it's a set of equations. So let me change the equations in a particular way. I want to change all the fermions into bosons, and under that circumstance, let's see what happens to our atom. You will note the electron clouds all collapse onto the atom. This would be a monumental disaster for life because chemistry relies on the fact that those lobes are there. If the lobes are no longer there, then all atoms behave the same. You cannot form chemistry. Without chemistry, there is no life. So this is a very important feature that we are very fortunate that our universe actually has this structure. Now, the other thing about the force carriers, there's one that I haven't said anything about. And in fact, in some ways, this force carrier may be viewed as perhaps the most mysterious or the most important of them all. This final boson is called the Higgs particle. It's rather mysterious. Let me talk about its role. In our table of the denizens, we had a list of their properties such as mass, and it might be useful for us to actually review that. So here are the denizens, the up and down quarks, charmed, strange, beautiful, and top quarks. So here are these objects. The masses on this table, as you can see, range from 1.5 in a set of units we physicists like to use, all the way up to 178,000 for the top quarks. For the electron, using the same set of units, the mass of the electron is about half an MeV, whereas the tau particle is about 1.7 MeV. So those were the quarks and the leptons. Among the force carriers, it turns out some are massive. The W, Z, and W plus, W minus, and Z are all massive. The photon has no mass. The gluons, which are the message carriers for the quarks, are massless. And then there's this thing called the Higgs boson. Leon Lederman, in fact, has coined the term for the Higgs boson, the God particle. And part of the reason for this is because of what it seems apparently to do in our universe. And we can, instead of talking about the equations, once again, it's much more effective for me to talk about what the effect of the Higgs boson in terms of a graphic. I'm about to run a graphic where on the left-hand side, there's a particle. And it's small, and that represents the fact that it has a little mass. It's going to proceed to the right, and you'll notice there's a series of circles through which it will pass. These circles represent the effect of the Higgs boson. And as you can see, as the particle passes through the circle, it gains in size. This is a graphical way of saying that it is the presence of the Higgs boson, we believe, that causes everything to get mass in the universe. That's why Dr. Lederman refers to this thing as the God particle, because without the Higgs boson, nothing gets mass. And if you don't get mass, then you don't get nuclear energies of the type that are associated with the weak exchange. And under those circumstances, again, our universe would be a very different place. So this particle, the Higgs particle, is critical. It's also been unseen. One of the things that my community of particle physicists will be endeavoring to do over the course of the next decade is to actually spot the Higgs particle in an experiment. We would have done this in the US had the superconducting supercollider been built. That was one of its primary purposes. Since it was not built, it turns out that the machine that is most capable of actually detecting the Higgs particle is called the Large Hadron Collider, or LHC. It's almost complete. Construction has been underway for a number of years, and very shortly in Geneva, Switzerland, the LHC should turn on. And one of its purposes will be to search for this mysterious Higgs particle that we think gives rise to mass. So we have fermions, we have bosons. All the bosons, which are force carriers, are responsible for holding objects, in particular our fundamental objects, in their shape. All of the objects, the fermions, are basically the stuff of which we build our universe. So this structure leads us to a number of rather interesting things. The pictures I've shown you so far pretty much could apply to little balls, but now we have to bring in a rather interesting aspect, and we've alluded to this several times. It's called quantization. What do we mean by quantization? The basic definition of quantization is that energy comes in discrete small packages, not in a continuum. Again, it's simplest if I talk about this in terms of what it does to the force carriers that occur in the theory. Remember from our previous lecture, the force carriers were objects that one could think about as carrying a message from one electron to another, or from one quark to another. And the message is either to be repelled or to be attracted, but it's a message carrier. That's its role. It was associated with this picture. This is, again, our Feynman diagram. And this particular one, we're talking about the message passing between two electrons that they ought to be repelled, where the particle of light, the gamma particle in the middle, is the message carrier. So that's our classical picture of how the forces work. In the quantum world, however, things get much more complicated. In the quantum world, particles are allowed to disappear and appear almost at will. In fact, the statement is that in the quantum world, anything that can happen must happen with some probability. Now, sometimes these probabilities are very small, and sometimes they're very large. In fact, the way that we view the quantum world is the things that we think are very familiar to us from the classical world are the things that are most likely to happen in the quantum world. But they're not always the things that happen in the quantum world. And one of the differences we can actually see in how the forces work. In this picture, the electron on the left actually emits two photons, one which is the message carrier that acts between the two, And then there is a second photon which it emits and then later absorbs. So this second photon has not sent a message to the second electron that it ought to be repelled. It is telling the first electron something that it must obey. So these kinds of pictures, well, they're easy to draw. Their beginning and end points are the same, but what's going on in the middle is very different. And just as I can draw this picture, there are even more complicated pictures that we can look at. This is a process that we physicists call vacuum polarization. In this process, once again, the first electron travels along and sends out its message carrier. The message carrier proceeds through space and time, and then at a certain point in space and time, it disappears. However, we know from physics that things just can't literally disappear. And in particular, the force carrier was carrying energy, and energy is certainly not allowed to disappear in our universe. So what happens to all of that energy? The idea is that in place of the force carrier, two particles which the force carrier act upon replace the force carrier. And that's the circle that we see appearing in the middle of the diagram. That's a particle-antiparticle pair appear. An electron and its antiparticle replace the original force carrier on the left-hand side of the circle. Now, particle and antiparticle have opposite charges. And as physicists have known for a long time, whenever you have objects with opposite charges, they attract each other. So although these objects are created at this point where the photon disappears, they travel in opposite directions, but they begin to feel an attraction to each other because they have opposite charges. This attraction eventually slows them down because initially they were flying apart. They become attracted to each other, and in fact, they recollide. And at this point where you get the collision, because they are precisely particle and antiparticle, they once again disappear. So it's a little bit like pulling a rabbit out of the hat and then stuffing the rabbit back into the hat. When they disappear, however, you have to worry about what happened to the energy they were carrying. Well, this energy, the energy is then inherited by a second photon, and it's this second photon which proceeds to the second electron and tells it you ought to be repelled. So this is a consequence of quantum mechanics, that the way things happen is not always the simplest way that we can conceive of them happening. Richard Feynman was the physicist who gave us this pictorial way of understanding what the equations of quantum theory are describing. The quantum world is a very different world in many other ways. So, for example, in our world, if I have a wall that's a certain height, in order to throw something over it, well, let's try imagining in an imaginary sense. In order to throw something over a wall of a certain height, if I toss it softly, the object rises to some level, but it falls back down. It doesn't get over. If I toss it a little bit harder, it gets closer to the top of the wall, but then eventually it falls back down. If I throw it with just enough energy, it makes it over the wall and goes to the other side. That's how the classical world works. Let's imagine that we shrink to the size of an electron, and instead of trying to throw a ball over the wall, let me imagine trying to throw an electron over the wall. It turns out electrons have a secret. Again, the wall that we can imagine is the same height. I try to throw the electron, and so if I throw it softly, well, maybe the electron doesn't make it over the wall, just like a baseball. If I throw it a little bit harder, but not so hard that if it were a baseball, it would get to the other side, so I throw it softer than that, it turns out that the electron may make it to the other side anyway. You don't actually have to throw the electron with the amount of energy that it takes to carry it to the other side of this barrier. This process is called quantum tunneling. And again, it is an aspect of the quantum world. So in the quantum world, things happen that are exceedingly unusual. Another example is we've all been out to a baseball game and there's a pitcher on a baseball mound who winds up and throws the ball to a batter. The ball proceeds in a nice, smooth curve that we physicists call the classical path. And the batter, of course, counts on this because the batter uses the classical path to try to hit the ball. Let's imagine that we can, again, can shrink. And instead of throwing a baseball, we have a miniature pitcher who's capable of throwing an electron. So once again, our pitcher winds up and now tries to throw the electron in precisely the same way that he delivered a baseball. Instead of the electron proceeding directly to home plate, the electron is, under most circumstances, will follow this path, but the electron is free to deviate from this path. In particular, instead of going directly to home plate, the electron might make a deviation to visit third base, choose to orbit around third base 137 times, and only after completing that 137th orbits, then decides to go to home plate. This sounds like something out of a cartoon. We see these sort of behaviors for objects thrown in cartoons, but you've never seen a real object behave in this manner. And so therefore, it leads to very great difficulty understanding that real objects can exhibit this behavior, but electrons do. They do it every day when you use a cell phone, when you use a computer, or any device that uses quantum electronics. So the quantum aspect of our universe, we have turned to our advantage with our new high technology. Well, so now we have this quantum world, and in the quantum world, we have to worry about the rules of nature being very different from the rules that we use in the world around us. Fortunately, these rules are such that in order to understand why things like electrons behave in this manner, we've come up with a picture which both means a story as well as a piece of mathematics. Let me remind you of one other story, something that can't happen in our world, but at least if we use balls, but can happen, for example, if we use sound. Again, we take our story of our pitcher who winds up and this time again throws a baseball. We expect the baseball to travel along a nice straight path. But let's imagine, instead of talking about the baseball, that we ask about someone shouting. In particular, if I stand and yell, the sound doesn't just go in a nice straight path. In fact, if I'm in a room with a door and someone's outside but not facing me but around the corner, they might still hear me. How is this possible? Why doesn't sound travel in a straight path? Well, this is something that science has had to deal with for several hundred years. Waves do not have to travel in a straight line. In particular, sound is a type of wave. And when sound gets to a barrier, instead of just simply passing by the barrier or being deflected by the barrier, it can bend around the barrier. This process is called diffraction. And this is something that we take advantage of in optics. It's a well-known behavior. And it is characteristic of waves. So waves are things that don't have to travel in nice straight lines. In the 1930s, a group of physicists used this analogy to understand why electrons were so strange in their behavior. The two physicists were Werner Heisenberg and Erwin Schrödinger. And what these gentlemen did was to write equations which in some sense, if you look at the history of physics, are the type of equations that had always been used to describe waves. But instead of describing waves, they said, these equations apply to electrons. So it's an assertion. And then when you write such equations, you can begin to make predictions. And one of the marvelous things that almost immediately happened out of this set of predictions was that we could understand why atoms had the structure that they do. Atoms, it turns out, if you heat an atom up, or more explicitly, provide energy to an atom, eventually it will radiate. And it radiates at very particular colors. It doesn't radiate at just any color. Each atom has a spectrum that is specific colors at which it radiates. When you apply this idea that electrons are governed by the equations that normally we think of describing waves, you find out that atoms must radiate in a particular spectrum. And so this was one of the first spectacular predictions of quantum theory, that we could understand why atoms radiate in the patterns that they do. With this prediction, you could then ask questions about what we physicists call fine structure. Some of the radiation has structure to it. So again, using this idea that waves and that electrons have properties like waves, calculations were made. Once again, spectacular agreement was found. So this is in fact the birth of quantum theory, and why, even though quantum mechanics is so far removed from our everyday experience, we can still say that prior to string theory, we had many experimental reasons to believe that quantum theory was an ultimate description of how our world works. Let me say a word about the word quantum, because that's something. Why do we even use the word quantum? Well, let me try to, again, speak of this in terms of an analogy. Normally, when we think of waves, we think of waves as being supported by some medium. For example, waves on the surface of water. And so whenever we have a phenomenon that's associated with waves, then you can think of gentle undulations, or, perhaps on a stormy day, what you find is that the waves are not just gently passing by, but in fact, sometimes a piece of the wave breaks off. Now, in the animation that I'm running now, we can sort of see this process where here's our waves, and then every now and then, imagine blowing on this with very great force, you could actually take a piece of the water and cause it to separate from the rest of the ponds, as we see here. So you get a little piece of the water that separates from everything else. Well, the word quantum is another way of saying a piece of something. Quantized means it comes in discrete packets. So the discovery that quantization is an aspect of our universe actually precedes 1930s and was discovered by Planck. If you look at the way light causes objects to heat up, and then look at the spectrum of the light that comes out of the object as it cools off, that spectrum has a very particular pattern. When physicists started thinking about this pattern, we were confused. Our calculations showed us that as the energy was increasing, we expected the pattern to flow in one way. On the other hand, when we did the experiments of actually heating objects up and then letting them cool down, we found out that the behavior was exactly opposite to our equations. This was a very great mystery for physics for a number of years until Planck came along. What Planck showed is that instead of thinking of light as a continuous wave, we ought to think of light in terms of discrete packets. They are quanta of energy according to Planck's interpretation. When this modification is made to our mathematics, then suddenly what we find is that the mathematical description of how an object radiates energy as it cools down or is heated up agrees exactly with what physicists had observed in the laboratory. And so Max Planck's great contribution to physics was the idea that things are not always continuous, that even energy must sometimes be thought of as coming in a smallest packet, and this packet is the quantum. In our discussion, we've been actually using the notion of the quantum without really thinking about it, because I talked about a message carrier carrying the forces back and forth. Well, the forces are also associated with energy. There's an energy associated with electromagnetic forces. There's an energy associated with the strong forces. There's energy associated with the gravitational force. If Mr. Planck's idea is correct, that energy comes in packets, then each one of these forces must be associated with energy that comes in a packet. These packets are precisely the message carriers that we've been talking about. So this picture of quantization and message carrier goes hand in hand and has the added benefit that when we apply this notion to the objects that we see in the laboratory, we are able to make predictions, literally tens of thousands of predictions about the way that quarks and leptons behave. And we have predictions from our mathematics, we have experimental observations, and to this point in time, the two of them agree to something like 9, 10, 11 decimal places. This is the best tested piece of science in existence. So physicists are absolutely convinced that our world at its most fundamental level is quantized. You will note, however, that I didn't talk about the graviton. We'll get to that in a later lecture. It turns out that quantizing gravity is nowhere near as simple as talking about quantization of the other three forces.